finally, we're going to turn our attention to the series-connected RLC circuit. And first, look at the natural response. So, initially, we're going to assume that there is some initial current I0 flowing through here with some initial voltage, plus or minus V0, and at t equals 0, the switch closes. We want to once again write the differential equation that describes the dynamics of this circuit. In this case, we'll write a voltage loop equation, and we'll do it V sub L, going in this direction and referencing plus to minus V sub L, plus to minus V sub R, and plus to minus V sub C. We have then, going in that direction, V sub L plus V sub R plus V sub C must equal 0. Now, the voltage across the inductor in terms of the current flowing through this series connection is V is equal to L times dI dt. Similarly, the voltage across the resistor is just equal to R times I, and the voltage across the capacitor in terms of the current is equal to 1 over C times the integral from 0 to t I of x dx plus whatever the initial voltage on the capacitor was. And so the sum of those things, those three things then, must equal 0. Now, once again, we've got derivatives and integrals. The way we got around that before is we differentiated both sides of the equation, and as we do so, we get then L times the second derivative of I with respect to t plus R times the first derivative with respect to t plus the derivative of the integral is just the integrand itself, so 1 over C times I, the derivative of the constant is 0, equals 0. Now, we divide both sides of the equation by L to get the coefficient in front of the highest order derivative be 1, and we're left with then the second derivative of I plus R over L times the first derivative of I plus 1 over LC equals 0. And once again, we have a second-order differential equation with constant coefficients. In this case, it is again homogeneous. The right-hand side is equal to 0. You'll notice this then is the same form or the same type of differential equation that we had before when we were talking about the series or the parallel combination. The only difference was that in the parallel circuit, the constant in front of this was 1 over RC. And as we went through the solution, coming up with the characteristic equation and solving for the roots of the characteristic equation, in that other case we defined, in the parallel case, we defined a constant alpha being equal to 1 over 2 RC. So we're going to spare you the details of solving this and going through that process, refer you back to the process when we did it for the natural response. But what we observe is that this equation here in terms of I is the same as the equation that we did before in terms of V across the capacitor, or V across the parallel combination, except that here this is R over L instead of 1 over RC. So just as we defined alpha to be 1/2 of the constant here, we're going to define the alpha for the series connected circuit will be R over 2L. And with that one change, the solution process to the series natural response is exactly the same as it was to the parallel natural response. Once again, we're going to be looking at the integrand. We're going to have the values, the roots of the characteristic equation, S1 and S2 are going to equal negative alpha plus or minus the square root of alpha squared minus omega naught squared. I should once again say that here, as it was in the parallel case, omega naught is equal to 1 over LC square root, the square root of 1 over LC. And once again, we have the issues of dampening. Here we're going to be looking at the case where alpha squared minus omega naught squared is greater than 0, it again is going to be overdamped. And the form of the solution for I as a function of t is going to be a1 e to the s1t plus a2 e to the s2t. Again, just as it was in the parallel case, and the s1 and s2 values are dependent upon alpha and omega naught, and we determine the coefficients a1 and a2 from the initial conditions. Then we have the case where alpha squared minus omega naught squared is less than 0. That will be the underdamped case. And once again, we're going to have the form of the equation be I of t is equal to e to the minus alpha t times the cosine of omega sub dt plus b1 times the cosine of omega sub dt plus, whoops, losing space here, b2 sine of omega sub dt, where, once again, omega sub d is defined as, where do I have room for it? Let's write it up here. Omega sub d is defined as the square root of omega naught squared minus alpha squared. It's known as the damped frequency. It's the frequency at which the ringing circuit oscillates. And then we have that final situation where alpha squared minus omega naught squared is exactly equal to 0. That's again called the critically damped. And we have I of t is equal to d1 t e to the minus alpha t plus d2 e to the minus alpha t. And as was the case in the parallel situation, all of the voltages and current flowing in this will be of this form. The only difference will be the values of A1 and A2, which will be determined from the initial conditions on whatever it is we're solving for.